Welcome to lecture 11. Today we will be talking about the frequency response of the amplifiers and why they are important for us and how we can find them. So basically we are interested into knowing about the speed limitation of the amplifiers. So when we want to work on a certain applications that they are at a high frequency, we cannot just design an amplifier and hope that it will work for these input signals, which they are at, let's say, gigahertz range. So you have the applications of, let's say, the Wi-Fi. It works at 2.4 gigahertz or 5 gigahertz. We have the Bluetooth at 2.4 gigahertz. You have the GPS, it's around 1.5 gigahertz. Some other application like the CPU or the radar can goes up to 36 gigahertz. So these high frequency application requires certain knowledge about the behavior of the amplifier and will they work for this high frequency signals or not. So in order to be able to answer this question that will they work or not, we need to understand the behavior of the circuit for with respect to the frequency, and therefore we can decide how it's going to behave. Okay, so if you remember, let's talk about the frequency response. And this is basically from chapter 11. So basically, if you have an amplifier and you apply a step input to it, let's say this goes from 0 to V1 and this is applied on the V input, and we want to see what happens on the V output. So basically, if your V out follows the input quite nicely, let's say this V2, that's an amplified version of V1, the certain gain of this amplifier A, and it looks like this, then this is a good or a fast amplifier. If the behavior looks something like this, that it tries to reach to the value of V2, and then once the Vn stops here, goes back down to 0, then it discharge back and behave like this. This is we call a slow amplifier, that ideally we don't want our amplifier to behave in this way. And this reminds you basically of the circuit, basic circuit composed of a resistor and transistor, a capacitor, sorry, R and C. And we are applying here a V input. That is basically a step response. What do you expect to see at the output? So we expect that V out tries to reach to the value of V1 here. This is 0. Tries to reach to V1, but with an exponential behavior, 1 minus exponential of minus t over tau, where tau here is equal to the value of RC, and this is, we call it the time constant. So depending on the value of this time constant, this rising time is going to change. So once you have, let's say, a small RC, typically desired, our output is going to follow the input in a faster way. So the way we will follow, this is, let's say, the value of the input or the maximum V2 that we want to reach. So depending on the time constant, we will have different responses. Sorry, it's going ideally starting when I observe from the same, starting from the same location. So this is one way and here this is another, or this is a third. So here this is tau 3, it's called, this is tau 1, and here tau, sorry, tau 2. So clearly that here the time constant tau 3 is greater than tau 2, greater than tau 1, and each tau here is the RC time constant of the circuit, depending on the value of the R and C in the circuit. So you can see that it's more desirable to have a low value of RC in order for the output to approach to the value, the desired value within a short time. Otherwise, if tau is large, then it will require more time, like the case of the black color here, in order to reach to the final value that is desired. And even in some cases, this behavior can be like a really bad, that, I mean, this on time might be quite small compared to this tau, and therefore the amplifier will not be able to settle to the I mean, it will reach to this point here, while this is not the final value that we are aiming for. So this can be a very bad situation. Therefore, we need to be careful on how to design our amplifier. Okay, so now we know why we want to study this behavior. I mean, we can try to find this equation for the time constant, but we can also look into it from the frequency domain point of view rather than looking at the time domain. So for example, if you still have the same circuit of the RC, and we have here V out, and we are applying a V input here. Remember that the impedance that's seen by a capacitor is 1 over SC, where as here we can assume is a J omega, in case when our input and output signals, are sinusoids. Okay, so we can assume it's just a J omega, where omega is frequency in radian per second. Okay, I think this information is familiar to you. Now we want to write the V out over Vn as a function of S, and we usually just call it H of S, or the transfer function. So this is equal like a form of a voltage divider, 1 over SC divided by R plus 1 over SC, which is basically we can simplify it in order to get rid from this. So it will be 1 over RC SRC plus 1. So this is our transfer function here. And we want now to find how this is going to change the magnitude of this transfer function with respect to the frequency. And that is going to be called our frequency response. Just want to remind you here that if we have a complex number A plus G times B, and want to draw the real part here and here the imaginary. So this is going to be A and this is B. So we can draw this vector here that has the magnitude equal square root of A square plus B square. Remember here we don't add the J part in the squaring, and the phase of this one is going to be equal to tan inverse of B over A. Now, similarly, here we can find the magnitude of this transfer function by applying the same relation, which is here for the numerator and numerator. So here the square root of 1 square is just equal to 1. And for the down part here, so just let's write it here, replacing the s with a j omega rc plus 1. So now we have it in a form of a complex number. So it will be the square root of omega square r square c square plus 1, all of 1 square, which is equal to 1. All of this is under the square root. So now I can plot this with respect to frequency, which is omega. So let me assume this is omega in radian per second. And here the magnitude of h of j omega. Okay, so at when omega equal to 0, this is going to be, this term will go to 0, and 1 over 1, which is 1. And then when this part term here, when omega goes very high, it's going to become a very large value. So 1 divided by very large value will lead to a small value. So eventually at very high frequency, it's going to approach to 0. And in the middle, it will just decrease. Now, this is an important one value here, when basically we call it the bandwidth. Let's call it, the value here of omega, where we basically cross this point here. I mean, where we have our amplitude equal to 1 over square root 2. This is going to happen. Let's see in the next slide. There's no space to write here. So when 1 over r square, square root of r square c square omega square plus 1 equals to 1 over square root of 2. And let's try to find this value out. So basically, we can square both sides and flip them. So we'll have r square c square omega square plus 1 equals to 2. And therefore, r square c square omega square equal to 1. And omega in this case, I will divide by r square c square and then finding the square root. So omega will equal to 1 over, sorry, no square root here. Just r and c, because they are also squared there. This value is very important, and we call it the 3 dB bandwidth. Why 3 dB? Minus 3 dB band. If you convert this 1 over square root into dB, how to convert to dB? It's 20 log of the value that you are looking for. So here, the 20 log of 1 over square root of 2, sorry, it will give you minus 3 dB. And this is a very important measure of the amplifier. At what frequency, basically, your amplitude of your signal, output signal, will become half of the maximum value. So again, at what frequency my output signal will become 1 over square root of the maximum value. This value also, it will be minus 3, if we are talking in dB, minus 3 dB of the maximum value. Means maximum value minus 3 dB. If my let's say my maximum gain is 60 dB, which is around how many times? 1000 times. Because this is base 10. So 20 log base 10 of 1000 is 20 times 3. And this gives me a 60 dB. So a gain of 1000 times is equal to 60 dB. Now, where to find the bandwidth? At frequency where my gain is going to become 60 minus 3 dB, which is at 57 dB. At what frequency my gain will be 57 dB? This is going to be called the 3 dB bandwidth of my amplifier. Okay. So therefore, it's an important measure. Now, just want to come back here. One more important note about it. Have you seen that here? Again, we are looking into the RC. So the RC is basically was the time constant. Where it went? The RC is the time constant of the amplifier, and 1 over RC is also the bandwidth of the amplifier. So you can see that the things are linked with each other. Both RC are coming in. So with a small RC, so 1 over RC, if this is a small value, means that 1 over RC is small, means RC is large, means large time constant, and 1 over RC small means small bandwidth, isn't it? Because the bandwidth here is 1 over RC. So if I have a small bandwidth, 1 over, I will have large time constant for the case of a smaller bandwidth. And this makes my amplifier slow amplifier. Okay, so now this means if I need to have fast amplifier, meaning I need to have a small time constant, I require my amplifier to be large bandwidth. Let's summarize this point again. So small time constant means large bandwidth. It will lead to a fast amplifier. Okay, so we need to keep these things in our mind when we design the amplifiers. Okay, now let's see if we should. Let's just summarize the points. So the frequency response will help us to study how much bandwidth our amplifier is going to have by looking at the representation of it and see when my amplifier will give me an out that it's equal minus 3 dB of the maximum value. So how to find we first need to replace S with J omega. J omega. And number 4, plot it to omega. Important that the drawing usually log scale. We try to plot it in dB. Okay, so that makes it's easier to view it and read it. Now let's just take one example. So example, I have this amplifier RD, if you remember. Now this is our favorite common source amplifier, slightly changed by adding some capacitor here called CL at the output, loading the output. And now we want to find, so we want to determine the frequency at which the gain falls by 10%. 10% here is almost equal to 1 dB, and assume RD equals to 1 kilo ohm, CL equals to 1 picofarad, and ignore lambda. Okay, now let's first, we want go back. First want to find the transfer function, and then we can go back to it. So the transfer function here, we go back and draw the small signal model. So this is 1 over CL times S, replace it with its impedance, and RD. Here I'm ignoring the R out because it's telling me to ignore lambda. GM V1, and here is Vn, and this is V1. So V out over Vn as a function of S, which we are going to call it H of S, is basically equals to minus GM times RD in parallel with the 1 over CL times S. And this gets simplified to minus GM RD over 1 plus, if you open this parallel combination, 1, and then replacing S with the J omega CL times RD. Okay, so this is our transfer function. Now we want to find the magnitude of this transfer function. So this here, sorry, J omega is equal to now the square root of minus GMRD square plus square root of 1 square plus omega square CL square RD square. Okay, which is basically equals to GM RD over 1 square root of 1 plus omega square RD square CL square. Okay, now we basically want to find when this magnitude of this transfer function falls by 10%. Falls by 10% mean becomes 90% of the maximum value. So what is the maximum value of this gain? What is the maximum value? The maximum value will occur when this omega is equal to 0, because this is the only thing that we can change. We have control here. We cannot in the circuit at this moment. Once we have designed it, you cannot change the value of RD or the value of the CL, but you can change the input frequency that you are applying. So when the input is DC, means there is the zero frequency, you can see that your denominator becomes the minimum value, and it becomes the maximum gain that we can get is a GM RD, because this is all zero, and GM RD divided by 1 is equal to GM RD. So when this becomes 0.9 of the GM RD, when it falls by 10%, means it becomes 90% of it, which is 90 over 100, it becomes 0.9. So what value of omega what value of omega gives us makes this relation correct? So we need to solve for this omega, and you can substitute the values and find that omega is going to become equal to 4.84 times 10 to the power 8 radian per second. Now, how you can convert it to hertz, frequency in hertz, you need to divide this number by 2 pi. So it's F equal omega divided by 2 pi, and this equal to 77.1 megahertz. Okay, now here, how we got this number, we just need to plug in, find the value of the GM, or here you don't need even to find GM. The GM will cancel with the GM, RD with the RD, and then you can just make square both terms and find the value. You have R, D values, you have CL values, you can find the omega value. Okay, so now this was an example to show you how you find the magnitude of the transfer function. Now let's move further and discuss an easier way of finding basically the frequency response of the amplifier without the need to know the transfer function in advance. And that's called the body plot. Now, the body plot depends on your knowledge of the poles and the zeros of the transfer function, and then you can draw the magnitude response of the amplifier, how it's changing with respect to the frequency. Now I will mention the rules and then we will discuss them, explain them through an example. So as omega passes pole frequency, the slope of the magnitude of h of j omega decreases by minus 20 dB per decade. So a slope of minus 20 dB per decade means that for 10 times increase in frequency, the magnitude drops by 10 times as well. Okay, now as omega passes zero frequency, the slope of h of j omega increases by 20 dB per decade. Similarly, for 10 times increase in frequency, the magnitude also increases by 10 times. Okay, I know that this is not clear, so I'm going to explain it further, but you need to remember that the pole frequency cause a decrease while the zero frequency cause an increase. Let's see what does this mean. Now you remember that transfer function, we can write it as a numerator function divided by numerator function, which is basically, we can assume it here, some A0, any value or gain, 1 plus S divided by omega Z1, 1 plus S divided by omega Z2, multiplied by 1 plus S omega Z and divided by 1 plus S over omega P1, 1 plus S over omega P2, until means the transfer function and h of s can be thought of as a function n of s divided by d of s, numerator over denominator. Now the zeros of n of s are called zeros of transfer function, while the zeros of d of s are called the poles of the transfer function. Okay. Now, so here we have omega z1, omega z2, omega zn are the zeros of our transfer function, while omega p1, omega p2, omega pn are the poles of my transfer function. Okay. So once we know that from the transfer function, we can draw the magnitude here in the log scale. And here the magnitude of h of j omega. So here I will have 20 dB. Sorry. This is in dB, the axis. And this value, oops, this value here, the maximum value is 20 log at the DC when all the S's are 0, 20 log base 10 of A0, this value of A0. Okay, so this is the maximum value that we can reach here at the DC. And so we will continue straight. If we find any, let's say, W pole, any pole, we will start at the pole frequency, we will start to decay with a slope of minus 20 dB per decade. Decay means 10 times. So if this is omega P1 and this is 10 times omega P1, we will have a difference here of from this value. If this was, let's say, 60 dB, the starting point here, it will become 40 dB, just as an example. If you find another, once we will find another pole frequency, let's say here, omega P2, once you will reach to it, the slope will become further steeper with a minus 40 dB per decade. So each pole will contribute to the accumulative value of the slope. Now, if you find a 0 here, WZ, it will contribute with a positive 20 dB. So this will become a less steeper with a minus 20 dB per decade. If you find another WZ, it will become a 0 slope. So every pole or 0 will add or decrease, will add or subtract a slope value of minus 20 dB or add 20 dB per decade to the previous value. We are starting from a 0 slope. Start from a 0 slope. Each presence of a pole will will decrease your slope by minus 20 dB. If you find another one, it will become minus 40 dB. If you find another pole, it will become minus 60 dB per decade. Now, the presence, or if you encounter any 0, your slope will be increased. So it will become positive 20, positive 40, positive 60. So it's you are accumulating based on your previous value of the slope that you are having. And therefore, this is going to give you a picture of the behavior of your amplifier with respect to the frequency. Okay, I think we can stop here and we'll continue next time. Thank you.